It's Shannon Methchick-Myers, and today we'll be checking out the vector space Rn. So in this section, we're going to learn basics about vector operations in R2 and then again in Rn. This way you can kind of see things that are familiar to you when you learn about vector spaces. Later on in the course, we will learn about some other vector spaces such as matrices and the set of polynomials, okay? Polynomial functions. So let's do it. Vectors in the plane. A vector is characterized by two quantities, length and direction. And is represented by a directed line segment. Geometrically, a vector in the plane is represented by a directed line segment with its initial point at the origin and its terminal point at some x1, x2. Now remember, that's just like x comma y. So if you have x1 comma x2, we're used to seeing that representing an ordered pair, right? But the notation I'm using is in the context that we are discussing this, this also represents a vector. It just depends on the context of the conversation. Now, the reason I don't use this notation here, which you're more used to probably for vectors, if you've had any experience with them, is because I will be using that notation to denote inner product later on, okay? So instead of, we use x1, x2 to represent the ordered pair or the vector with terminal point x1, x2, depending on the context. So it's kind of like if you have an interval from -1 to 2, an open interval from -1 to 2, you could also use that to represent the ordered pair -1, -2. It just depends on the context of the conversation or the application. All right? Okay, so both these lowercase letters often designate vectors when you're using a computer, all right? But when you write them by hand, you need to write an arrow above the letter designating the vector. So I'll be using arrows above to designate vectors, and you will need to do that so too when you're writing your exam solutions. Okay, so let's take a look at a picture of this. So if we just have some, we've got our coordinate plane here. And if, oops, that's not very, so we have our, coordinate plane here. And I'm just going to randomly pick. So let's just say this is x1 and this here is x2. So if we start at the origin, right, for our vector, basically what's happening here is it's like you have a ray that is rotating. So if you kind of look at it in this lens, if you think about a ray, say that starts here, some ray starts here, and then it rotates. It's like doot, 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 like my sound effects. And then it ends up, its terminal point is about there, right? And so you end up with this vector. So this vector, let's call this vector x, and it's equal to x1, x2. Cool, cool? All right. So that's our rotation. All right, so here we go. The same order pair used to represent its terminal point also represents the vector. So this is kind of what I was saying above. That is x equal to x1, x2. The coordinates x1 and x2 are called the components of the vector x. The vectors are two vectors in the plane, u equals u1, u2, and v equals v1, v2, are equal if and only if, what do you think? Beautiful, u1 equals v1 and u2 equals v2. So each corresponding component needs to be equal for the vectors to be equal. What do you think the 0 vector is for R2? What do you think? Good. We would just write a 0 with an arrow over it, and it's going to be 0, 0. So it's just really, it has no length at all. It has a length of 0. How about R3? Awesome. That would, look how the 0 with the line over it doesn't change, right? But since we know now that we're in R3, it's going to be terminating at the origin. Cool, cool. And this is an important fact to remember as we move on in the course. Sometimes the notation looks the same, but its reality is a little bit different. So notation meaning the 0 with the line over it, or the bolded 0, if you're looking at typeface, is the same for all. But do you see their actual components? The number of components differs drastically. Okay, so now our n, again, you'd notate it the same on the left side, but what it actually looks like is you'd have 0, 0, 0, all the way down to 0, and there would be n 0 components. Or let's say n components which are all 0. Okay, so let's look at the first example. This is just to kind of warm us up and take a look at how we can represent these geometrically. It's really important to get big picture idea with R2 and R3, because as we move on to more dimensions, I mean R10, we're not going to be able to draw a picture of it. So you're going to have to really get to know these ideas about vector spaces and be comfortable with them in R2 and R3 and the pictures they represent, so that when you are in the dimensions that we can't picture, we can still perform operations with them and have an idea of what's happening. Cool? All right, so here we go. I'm just going to use the same scale for all of these because I wanted to give you an idea of how things, change. So I'm just, these kind of grids that I use, if each line is a tick mark, it's always a square, 10 to negative 10 on each axis. All right, so this first one we'll do in blue. So all you do is you plot the terminal point. So that's 1, 2, 3 to the right and 2 down. And that's our vector u. So u equals, or terminates at, 3, negative 2. That's our vector u. Cool? Alrighty. So next up, let's picture this vector v. Use a different color for v. So vector v terminates at 2, 1. So 2 to the right, 1 up. So our vector v looks like this. All right, terminates at 2, 1. Groovy? So here's a bigger image of both. So here was what our vector u looked like and our vector v. Cool so far? Awesome. Now, let's take a look at what happens if you add these two vectors, right? If you add these two vectors, it's really cool because it forms like a parallelogram. So in this, the sum is going to be the vector that terminates at the corner of the diagonal. So let's see what this looks like. So you start with the first one, all right, and which was u, and you draw that vector. So we've already done that. 1, 2, 3 to the right and 2 down, right? And then it looked like this. And then again, the axes will be the same, or the scale will be the same, rather. And then if I add v, to it, basically what I'm doing is I start v at the terminal point of u, and then I draw it. So v went 2 to the right and 1 up. So it'll now terminate at this point, okay? Well, I'm not going to complete it. I'm not going to complete it. So what ends up happening is you end up having a situation where you can literally make a parallelogram, and what that means is that you would have this other u, that would go here, and it would be up 2 from there and over 3. I'm going to dash this one in. And then the v has its own, you know, kind of shadow here, and that would go like this. Good so far? So it's called the resultant vector. Resultant vector is going to be the vector that terminates at the diagonal right there. And that vector is named u plus v. You can name it some other vector if you want. And that terminates at the ordered pair 1, 2, 3, 4, 5, negative 1. Cool, cool? All right, so now you might have noticed something. You might have noticed that if I were to look at this, I could do this algebraically, right? I could say that u plus v, I'll do it in the purple again, u plus v. Well, what if I wrote it in its component form? And this would have been 3, negative 2 plus, and v was what? 2, 1. And that ends up being one happy vector, okay, where I add the corresponding components. So 3 plus 2 will be the first component of the resultant vector, and then negative 2 plus 1 will be the second component of the resultant vector, which gives us, lo and behold, 5, negative 1. So there you've got your algebraic way of doing it, and we've shown you the geometric way, or geometric representation. Okay? All right. Going okay so far? Awesome. So now we're going to take a look at scaling a vector. So if you scale a vector, you're multiplying it by a non-zero constant, So here, if it's scaled by a negative, it's going to go in the opposite direction that it started, and it'll be scaled by the absolute value of, you know, the coefficient. So here we go. Let's draw our v vector again, and remember that was at 2, 1. All right, and that was v equals 2, 1. Now I'm keeping it small right now so that you can see the comparison. I'll zoom into it in a moment. So now when I scale this, I'll have the opposite direction, but it's going to be doubled, right? It's 2 times as much as. So here, one times as much in the opposite direction would take us here. Correct? So 2 times as much will, in the opposite direction, terminates here. And so we'll have our vector that's been scaled by a factor of negative 2. And so this is going to be negative 2v, and don't forget your vector notation, is equal to, let's see where it terminated, 1, 2, 3, 4, negative 4, negative 2. So here's what it looked like when we scaled it in a negative direction. Groovy? So they're still on that same line, all right, if you will, but it's just been scaled. All right, so now moving right along, Oh, actually, no, let's check this out. So continuing like we did before, we can also do this algebraically. So negative 2v is equal to negative 2 times the vector v in component form, which was showing where the vector terminated when drawn from the origin. So we end up with the negative 2 can come in, and it goes into each component. And so we end up with negative 4, negative 2. And that goes both directions. If you started out with the vector that terminates at negative 4, negative 2, right, you could pull out a negative 2 and write it the way that we wrote on that first line. All right, so here we go. Next up, here's some important vector spaces. It's not all of them, but here's a few of them. All right, these are examples of important vector spaces that are in Rn. So R implies R1, and that's considered one space, and it's the set of real numbers. So if you were visualizing this, it would just be a single number line. R2 is 2 space, 2 dimensions. And so now you have the set of all awesome ordered pairs of real numbers. R3 is 3 space, 3 dimensions. And that's the set of all ordered great triples of real numbers. And then continuing on in that vein, you've got Rn, that's n space, and that is the set of all ordered n tuples, okay, of real numbers. Groovy? All right, so the definition of vector addition and scalar multiplication now this is for Rn. It's better just to do it in general because R2 follows this. So if we let U equal to U1, U2, ... all the way down to UN. So all the UIs are real numbers, okay, because they're the components of the vector. And if we let V equal to V1, V2, all the way down to Vn, and they're going to be vectors in Rn, and we're going to let some C belong to the real numbers. Then the sum of U and V is defined as the vector. So when you add 2 vectors, you get another vector, and U plus V is equal to U1 plus V1, U2 plus V2, all the way down to UN plus, Vn, and the scalar multiplication of U by C is defined as the vector. So a scalar times a vector gives you another vector. C times U is equal to CU1, CU2, all the way down to C times UN. You're done. Cool, cool? All right, so properties of vector addition and scalar multiplication in Rn. We're going to do some of the proofs for these, all right? And these are proofs that are kind of so easy they're hard. And what I mean by this is that you do not know, quote unquote, know the properties for vectors, but you do assume true the properties for real numbers. So what we're doing here is we're doing it's called direct proofs here, and we're starting with vectors, putting them in component form, typically making them one happy vector, doing the operation that you're trying to prove in real numbers, right? Because we can assume those, breaking them back apart into vectors, right? And so remember that we assume what? We assume properties for real numbers like associativity, commutativity, identity, inverse, that kind of stuff. And what we need to show is what happens for vectors. So let's do it. In order for this to be easier and where we don't need to identify vectors each time, what the vectors look like each time, let's identify them now. All right, so we're going to need a vector u, v, and w. All right, and we're going to need one scalar, or is it two scalars or one scalar? Two scalars, c and d. So we're going to let u equal to, so we're doing all of these in Rn. So u1, u2, all the way down to un. V will equal to v1, v2, all the way down to vn. W will equal to w1, w2, all the way down to wn. Such that ui, vi, and wi belong to the real numbers for I equal 1, 2, down to n. And we'll let C and D also belong to the real numbers. So we have the setup for all of these proofs. Okay? So here we go. U plus V turns out to be a vector in Rn. This is considered closure. So the first 5 properties are addition, and the second 5 properties are for scalar multiplication. So this closure property, it basically means for addition that if you start out with 2 vectors that are in your space, Rn, and you add them, you'll end up with a vector in Rn. Okay? So we're allowed to use properties for real numbers, and we're also allowed to use definitions in proofs, right? You don't have to prove definitions. So we're going to be using the definition. We can show the definition for, or we've shown the definition for vector addition and scalar multiplication, all right, for Rn. So here, we'll use that along with properties of real numbers to do these proofs. Groovy? All right, so the proof for this is direct, and we're gonna just use properties of real numbers in algebra. So here we go. U plus V equals. So first step, good, put it in component form. So U1, U2, all the way down to UN plus V1, V2, all the way down to Vn But by definition, what is that? Definition of vector addition, we know that this is u1 plus v1, u2 plus v2, all the way down to un plus vn. Remember that it was definition of vector addition basically says you add corresponding components in the vectors. So what is this? Beautiful. This is a vector in Rn. So sometimes people have a little bit of trouble with the closure proofs because actually, yeah, that's fine. Some people have a little bit of trouble with the closure proofs because of the fact that they are kind of a so easy it's hard thing. So just wrap your brain around it. You're going to really need to ponder this material. This is a very abstract class, okay? So you're going to need to think about this material and ideally talk about it with people. All right, so in order not to mix up the proof stuff with the basics, like the statements, I'm going to do those in a different color. So we're going to say u plus v is a vector in Rn, and that was called closure. And then now u plus v turns out to be equal to v plus u, the vector v plus vector u. And what property do you think that's called? Good, commutativity under addition. And I already said this was addition here, all right? So we don't have to restate it. So the proof for this is going to be, how would we do it? Awesome. It starts out the way it was before in the previous proof, right? You start with the sum of these two vectors and you put them into component form. And yes, you have to do all the steps that I've done. Okay, so, and this one from the last time, this was by definition. Okay, so this one, again, by definition of vector addition, is going to be u1 plus v1. Oops, u2 plus v2, all the way down to un plus vn. And remember, all the components are real numbers, right? So again, this is by definition. Now, here's where we get to, depart from the prior proof. We need to do another line. And that other line is going to be what? Perfect. We know the real numbers are commutative, right? So now that we have it in component form, we can commute each of these sums. And we're able to do that because the set of real numbers is commutative. And again, we're in addition, so I'm not going to restate that. All right. Well, what is that? We now have it in as one happy vector, right? But now we need to split it into two vectors. So this will be v1, v2 all the way down to vn plus u1, u2 all the way down to un, and that's using the definition of vector addition again, going the other way. And this, of course, is v plus u, which is what we were trying to show. So a lot of times, you end a proof by putting two little lines in a book. You'll often see a box. If you want to get fancy, you could do QED, which basically is the Latin phrase quod erat demonstrandum, I think. And it literally meaning is what was to be shown, right? So I used to like to put that one. Cool. All right. So basically you want to show that your proof is finished as you move along. All right. So I'm not going to do the proofs on every single property. Some of them are left to quizzes or optional homeworks, but I've picked a few in here to do. So let's check it out. U plus the quantity v plus w is equivalent to quantity u plus v and then plus the vector w. So this is the beautiful associative property, and that's under addition still. And the vector u plus its zero vector, right, the zero vector that's in its space, is going to be just the vector u, and that's the additive identity property. Okay, now u plus the vector u plus negative of the vector u, or the opposite of vector u, is equal to the zero vector in its space, and so that's the additive inverse property. So the zero vector is the inverse element for vector addition. All right, just like 0 is the inverse element for R, the real numbers under addition. Groovy? All right. So scalar multiplication. So again, that proof would be very similar to the number 6 would be very similar to what we did in the first one. A scalar c times a vector u needs to be a vector in Rn. And so that is the closure property for scalar multiplication. Now we're in scalar multiplication. And then a scalar times a sum of vectors is equivalent to the scalar distributed to each vector. So there's actually two distributive properties. So to do the proof of this one, what do you think we should do? Beautiful. Start with our left-hand side. Again, we've already identified what the scalar c is and what the vectors u and v are. So we can just start it off. So this will be c times. Now what we want to do is put those vectors in component form, right? And still have the parentheses or the grouping notation around the sum. So u1, u2, all the way down to un is the component form of the vector u. And then v1, v2, all the way down to vn is the component form of vector v. And yes, you need the grouping symbols, and no, you can't just bring the c in already because we're still dealing with vectors. We can only bring that c in and apply the distributive property when it's all in terms of real numbers. Cool, cool? All right, so let's do it. What do you think we ought to do? Awesome. Why don't we write that sum as one happy vector, okay? And that would be using the definition of vector addition, right? And actually on these, let me be a little more specific. Whoops, that was fine. All right, so this one here was by definition of vector addition. Set of real numbers is commutative. Definition of vector addition again. And then down here, we'll do the same. Specify the definitions. And the reason I'm doing this is because we're going to use both of them. All right, so now the definition of vector scalar multiplication said that we can bring the c into each component of a vector, right? So be careful because you're going to have c times the quantity u1 plus v1. Can't use distributive yet. C times the quantity of u2 plus v2. And we're using definition of scalar multiplication. All the way down to c times the quantity of un plus vn. Definition, vector, scalar mult, meaning multiplication. All right, finally now we can use the distributive property. So when we do so, we'll end up having cu1 plus cv1, because we can do that because we're in the real numbers. And we assume those properties. cu2 plus cv2 all the way down to cun plus cvn. And this reasoning is because the set of real numbers is distributive under multiplication. All right, so next up, what do we do? Well, we've got a vector sum, right, as one happy vector. So let's break them up, all right? So now this will be cu1, cu2, all the way down to c times un plus CV1, CV2, all the way down to CVN. And that's by what? Great. Definition of vector addition. All right. But what is this one? This is C times U1, U2, all the way down to UN, plus C times V1, V2, all the way down to Vn. And now this one is what? Definition of vector scalar multiplication. And then finally, sorry, I didn't leave enough space here. I thought I had. This is equal to C times U plus C times V, which is what we were trying to prove. Groovy? Okay, so the next property, it would be a similar proof except a little bit easier because you're only using one vector and you're using two scalars. But quantity C plus D times the vector U turns out to be C times U plus D times U. And this again is the distributive property. And then use our associative property, C times the quantity, D times the vector U, is equivalent to C times D times the vector U. And that is the associative property under scalar multiplication. And you know, it's funny, a lot of times, you know, students don't remember these properties, but you use them all the time, okay? So try to, when you're doing operations, try to think about, oh, what property am I using in my head, or properties am I using in my head when I'm computing this? And you'll be surprised. All right, so 1 times the vector U is equal to U, and that is the what? Multiplicative identity property. And notice there's no multiplicative inverse property. That's important. And there's no commutativity property for vector multiplication. And that's important as well. Here we go. So we're done with this, and just a note here, 1 is the identity element for scalar multiplication. Example 2. So now let's do some computations with this. And if you want, feel free at any time to pause the movie and do these yourself and then check your work. All right. Now, if I asked you to do basic computations, our first exam is going to probably be without the calculator. So you wouldn't need to show as much work as I might be showing. All right. So let's go ahead and work with these and kind of go from there. All right. So W plus U is equal to negative V. So we want to isolate W and figure out what it is. So here, what we're basically going to do is we're going to I'm going to rewrite this where I have more room. And we're going to be adding negative the vector u to both sides of the equation. And then what's going to happen, we'll get w plus the 0 vector, not just 0, is equal to negative v plus negative u. Cool, cool? Notice we haven't defined really a subtraction yet, so I'm going to do these properly. We know that w plus the 0 vector is just w from the properties above. And hey, can't I factor out a negative 1? You can just say a negative, but I could factor out a negative 1, right? And then I would just have this vector sum, v plus w, or v plus u, I apologize. So w will be the negative of the sum v plus w. V in component form is negative 1, 8, 0, and 3. And u in component form is 2, negative 1, 3, and 4. So again, just switch them. And then w will be, I forgot to close my grouping, w will be negative of, so negative 1 plus 2, I'm adding corresponding components, 8 plus negative 1, 0 plus 3, and then 3 plus 4. And on an exam, I would expect you to really be doing this in your head, but it's good the first couple of problems that you do just to work it out like this, because then you know what's going on when there's not real numbers or constants in here, right? If there were variables in here, this would look a lot scarier. All right, so completing the additions, I'll have 1, 7, 3, and 7 for an end result for w of negative 1, negative 7, negative 3, negative 7. Cool, cool? All right, so on to the next one. Dividing line here. And we'll have w plus 3 times v is equal to negative 2 times u. So if we rewrite this, we will have w plus 3v, I'm going to leave a space, is equal to negative 2 times u. So again, what should I do? I should add negative 3 times v, the vector v, and then let's see what we get. So we'll have w plus the 0 vector is equal to negative 2 times u plus negative 3 times v. So w plus the 0 vector is just w, right, by additive identity. And then I'm going to put these vectors now in component form. So negative 2 times u, so u was 2, negative 1, 3, 4. And then plus negative 3 times v. And v was negative 1, 8, 0, 3. I'm going to bring this w back here so we have enough room to complete the problem. And so we'll have the vector w will be, so negative 2 is our C for the first part, and we'll have negative 2 times 2, comma, negative 2 times negative 1, negative 2 times 3, negative 2 times 4, plus, now bringing the negative 3 in, we'll have negative 3 times negative 1, negative 3 times 8, I am going to run out of room, negative 3 times 0, and negative 3 times 3. Sorry about that. That's all one vector. So negative 3 times v, just so that since this is sloppy, you've got here. Cool, cool? All right. So now w will be equal to negative 4, comma, the vector, negative 4, positive 2, negative 6, negative 8, plus positive 3, negative 24, 0, and negative 9, which will give us the vector negative 4 plus 3, comma, 2 plus negative 24, comma, negative 6 plus 0, comma, and negative 8 plus negative 9, which finally is negative 1, negative 22, negative 6, and negative 17. So I recognize that you probably did this in a much shorter amount of time, which is fine, but I wanted to show you how we're using the properties. All right? So next up we have definition of column vector addition and scalar multiplication. So here, let u1, u2 all the way down to un, and v1, v2 all the way down to vn, and c be scalars. So if you're adding any two columns, it's really the same type of situation. In fact, once we learn about transpose, you'll learn that, the transpose of a row vector is a column vector and vice versa. So these both go along in the same way, but I thought it was worth rewriting it so you can see it in this manner. So now let's go ahead and do these. I'm going to go a little bit faster with these examples. So if you want to pause the movie, go ahead and then check and see how you did. All right, so let's do this thing. 2 times u minus 3 times v. So this will end up being equal to, so first I'll do the 2 times u, and that would give us what? Negative 6, 36, negative 2, 62, and negative 18. And then I'm going to write this as plus a negative. Okay, so we're going to, because we haven't defined subtraction yet, and actually subtraction is always, in real numbers, it's defined as adding the negative or adding the opposite. So negative 3 times v is what I'm doing. So I'm really doing 2u plus negative 3 times v. So then when I do that, I'll have 6, negative 123, negative 3 times negative 6 is going to be 18, 9, and negative 45. Cool, cool? So, just highlighting, negative 3 times v is this whole result here, the vector and everything. And 2 times u is this result here. And now we want to get one happy column vector. So what will happen? We will get, beautiful, 0. And then I add 36 and negative 123. I believe that we will get negative 87, positive 16, 71, and then what's going to happen? We're going to get negative 63 for the last component. Cool, cool? All right, and then B, negative V plus U. So I'll solve it as that. That will end up being equal to negative. So if I add V plus U, first I'll have negative 3 plus negative 2 is negative 5. Actually, it's really reversed. Negative 2 plus negative 3 is negative 5. But what do we know? We know that vector addition is commutative, right? So we can commute them. So we would end up with the second component is going to be 59. The third one will be negative 7. Fourth one will be negative or positive 28. And then positive 6. And so that's our V plus U. All right, so now I just bring that negative inside. So then this will make the 5 will be positive, and then we'll have negative 59, positive 7, negative 28, negative 6. All right, so how you doing? Don't forget to pause the movie and get up and stretch when you need to. All right, so here we go. More properties. All right, so properties of additive identity and additive inverse. Again, these are all fair game for the exam, these types of proofs. So the additive identity is unique. Okay? We will do quite a few proofs about uniqueness. And a lot of times what happens is that you say, hey, suppose there's another one out there. Suppose it's not unique. And then what will happen is you'll show that, like in this case, you'll show that it's the 0 vector, right? So just kind of follow along, but that's the evil plan, right? Whenever you're doing a uniqueness proof, or usually when you're doing a proof about uniqueness, you suppose there's something else out there that also, satisfies this property. And then you show, no, it's equal to whatever that element was. So let's do it. Suppose there exists, so the backward capital E means there exists, right? So suppose there exists some U that belongs to the R set of ordered n tuples, okay? Such that, so this backwards epsilon means such that. Some vector V plus the vector U is equal to the vector V, all right? Okay, so, and V's already been defined to be a vector in Rn. We don't need to get this in component form because we can use our properties from the earlier theorem. So going from this equation that we started with and leaving some space, we want to figure out what U is, okay? All right, to see if there is another identity out there, additive identity out there. So we want to isolate the U. So if I add a negative V, vector V, to both sides, then I could commute them, right? So them meaning the U and the negative V, the vector U and the vector negative V. So then I would have this. So now, what is V plus negative V? Beautiful. It's this zero vector. So V plus negative V is a zero vector. And that's from that theorem above. And the left side is where we can do that because vector addition is commutative. Now, here we go. V plus negative V again is the zero vector, right? And if I add U to that, I'll still have the zero vector on the right side. So again, it's the same operations. I'll use the same highlight. And the zero vector plus any vector is just that vector. So the vector U has to be the zero vector. Well, what can we conclude from that? Well, therefore, the additive identity is unique. We tried to find another one out there, but we just got the zero vector again. Groovy? Okay, so the next ones we won't prove because again they'll either be maybe quiz problems or homework problems. But here are the properties. The additive inverse is also unique. The scalar 0 times the vector V is the zero vector. The scalar C times the zero vector is also the zero vector. So if you have a scalar times a vector V and it's equal to the zero vector, then what has to be true? C would have to be the scalar 0 or what? The vector V would have to be the zero vector. And you could have a case where C was 0 and the vector V was the zero vector. Okay? So, the opposite of V is just V, or the negative of V is the vector V. Okay? So those are all the properties. Now, linear combinations of vectors. An important type of problem in linear algebra involves writing one vector as the sum of scalar multiples. This is super important. Super important for you to get this down. Of other vectors, V1, V2 down to Vn. Now notice these V's are bolded, okay? So before, what have we been doing? We've mostly been doing the subscripts when we were in component form. Now these are each vectors. Vector V1, comma, vector V2, all the way down to vector Vn. Cool, cool? So if we call the vector x the sum of scalar multiples of all these v's, it would look like this. So the scalar doesn't have to be the same. It could be, but it doesn't have to be. So we'll just write it like this. And it goes all the way like this to Cn times the vector Vn. And that is called a linear combination. That meaning x of the vectors vector v1, vector v2, all the way down to vector vn. All right, so if possible, let's write u as a linear combination of v1 and v2, where v1 equals 1, 2, it terminates at 1, 2, and v2 terminates at negative 1, 3. So, all right, let's check it out. So we've got our first one, part A. So, and again, it's good to start these out where you're writing things in general so you can see what they look like. So we want to see if it's possible to write the vector u as some constant c1 times v1 plus some other constant c2 times v2, right? Well, we have some of this information, don't we? The vector u is 0, 3, or terminates at 0, 3, and then putting in v1 and v2, we'll have c1 times 1, 2 plus c2 times negative 1, 3. So I just put in what did I use last time? So vector v1 is the vector 1, 2, and vector v2 is the vector negative 1, 3. And this time our vector u is going to be the vector that terminates at 0, 3. All right. So, all right, 0, 3 is going to be, well, can't I rewrite this as c1 times 1, comma, c1 times 2 plus c2 times negative 1, comma, c2 times 3. I'm just following the definition for scalar multiplication. So that's going to give us that 0, 3 is equal to 1c1 is just c1, 2c1 plus negative c2, comma, 3c2. All right, then on the right side we're going to be using vector addition to make one happy vector. So the first component will be c1 minus c2, and then 2c1 plus 3c2 is the second component. Now, utilizing our mad knowledge about vector equality, what does that mean? Beautiful. That means that c1 minus c2 has to equal to 0, and 2c1 plus 3c2 has to equal to, great, 3. So now, just showing you what happened here, find more colors. I'm equating c1 minus c2 to 0, and I'm equating 2c1 minus 3c2 to 3. Cool, cool? All right, so what do I have? Oh my goodness, I have a system of equations, right? So now here, how do you want to solve this? Isn't this going to be, if I put this into a vector, right? I'll get the augmented vector, what? 1, -1, 0, 2, 3, 3. Good so far? I'll do the other problem on the next page. So now, what operation would I want to do? I'll do this one by hand. Awesome. -2 row 1 plus row 2 for a new row 2. And so we will we'll rewrite the first row unchanged. And then we'll write in our new second row. So we'd have -2 plus 2 is 0. And then we'll have a +2 plus 3 is 5. And then we'll have 0 plus 3 is 3. This is the system, or equivalent to the system. C1 minus C2 equals 0. And 5C2 is equal to 3. So this is going to give us that C2 has to be perfect, 3/5. And that would mean that what would happen with C1? So doesn't C1 have to be equal to C2 to get that result? So C1 will also be 3/5. All right, so what have we found? We found that yes, it's possible, right? And so we found that the vector u, which was 0, 3, is equal to 3/5 times v1, which was 1, 2, plus 3/5 times v2, which was -1, 3. Isn't that cool? And you can also check it out. I mean, if you check this out mentally, you'll see that you do get 0, 3 when you do the computations on the right side. All right, so we're done with this problem. And now we're gonna do okay, so let's take a look at part B. What we will have going on now is we've changed our u, but we kept our v1 and v2 the same, all right? So again, we want to find out if there's a way to write u in terms of a linear combination of v1 and v2. So this is always how we're going to set that up. And, we need to substitute in what we've got. So this time u is 1, -1. So that would equal to C1 times V1 was 1, 2. And with C2 times, you'll have V2 being -1 and 3. And this is what we've done before. This was our V2. This was our V1. And we have a different U this time. We can write 1, -1 as C1 to C1 plus -C2 comma 3C2. So 1, -1, this vector would be equal to, writing as one happy vector, we'd have C1 minus C2 comma 2c1 plus 3c2. So the right-hand side's the same. Equating, we have c1 minus c2 has to be equal to 1. And 2c1 plus 3c2 has to be equal to negative 1. Cool, cool? This corresponds to the vector, to the matrix 1, negative 1, 1, and 2, 3, negative 1. This is augmented. So, well, let's do 2 row 1 plus row 2 for a new row 2. And let's see what we get. We'll get the first row stays the same. And our new second row will be 0. Negative 2 plus 2 is 0. And then positive 2 plus 3 is 5. And then we'll have negative 2 plus negative 1 is negative 3. Cool so far? Great, great. And bringing this back into a system, this is equivalent to C1 minus C2 equals 1. And 5C2 is negative 3. Excuse me. So, when I isolate C2, I'll get negative 3/5. And when I plug in the negative 3/5 in for C2, I'll have C1 minus negative 3/5 has to equal to 1. So C1 would equal to 1 minus 3/5, which is 2/5. So this one works out too. Isn't that amazing? So it's not unique how you can write a linear combination, which is another important concept. So what did this linear combination look like? It looks like 1 negative 1 is equal to 2/5 times V1, which was 1, 2, and then minus 3/5 times negative 1, 3. Now, a lot of times what we do, here's kind of a note, all right? So, by the way, this is the answer to this problem. And just keep in mind that a lot of times what we do is we write a set of vectors. So a set S, right, equal to some set of vectors, V1, V2, if you have this going on. So if you can obtain any vector in R2 using a linear combination, of the vectors in S, then S is a spanning vector, or a spanning set, in R2. So just kind of keep that in mind. That's what's coming up. All right? Okay, so our next example, example 5, we've got vectors in R3 this time. So let's check it out. Again, we're doing the same kind of thing. We've got our u, and we want to know, does our vector u equal to some constant times vector v1 plus some other constant times vector v2. All right, so let's do it. U was negative, or is negative 1, 7, 2, and we want to see if we can find constants where when you multiply a constant 1 to v1, which is, oh, sorry, we're in R3, so that'd be C3 times v3. So v1 is 1, 3, 5. v2 is 2, negative 1, 3. And v3 is negative 3, 2, 4. Cool. As negative 4, sorry. All right. So again, you know, these are the different vectors. Our vector v1 this time is 1, 3, 5. Vector v2 is 2, negative 1, 3. Vector v3 is negative 3, 2, negative 4. And then our u vector is negative 1, 7, 2. And those are what was given in the problem. So, same thing we did before, just one additional term. So we'll have, bringing the C1 in, we'll have C1, comma 3C1, comma 5C1. And then plus 2C2, negative C2, and 3C2, plus negative 3C3, 2C3, negative 4C3, and then making one happy vector, we'll get C1 plus 2C2 minus 3C3, comma 3C1 minus C2 plus 2C3, comma 5C1 plus 3C2 minus 4C3. Cool? And then just like before, we will equate corresponding components. We've got one vector on the left side and one vector on the right side, so we can equate corresponding components. So C1 plus 2C2 minus 3C3 has to equal to negative 1. 3C1 minus C2 plus 2C3 has to equal to, awesome, 7. 5C1 plus 3 minus 4C3 must equal to 2. Good so far? Awesome. So this one has the matrix, or corresponds to the matrix, 1, 2, negative 3, negative 1, 3, negative 1, 2, 7. And our third row will be 5, 3, negative 4, and 2. We'll have this augmented matrix. And the reduced row echelon form, let's find out what that is using some technology. So we'll go ahead and go to, what the heck, we'll go to Octave. B is equal to what was it? We had our first row was 1, 2, -3, -1, and then 3, -1, 2, 7, and our third row is 5, 3, -4, 2, and when I hit return, you can see that that is our matrix, and then you just double check it with your work. And what we want to do is find the reduced row echelon form of our matrix B. And we get this matrix here. Okay, so we're back, and this is what we got for our result in Octave, right? So let's put it down here, and then we can double check that I entered in the correct matrix. I think we're good. Yes, awesome. So this matrix I'm writing right now is equivalent to the matrix we started with. Okay, so here we go. This is why it's always good to go back to the system, because you're going to get C1 plus, and this is, I'll approximate this, 0.14. C2 is 0. And we add C2 minus approximately 1.57. C3 is 0. And then over here, 0 C1 is 0, plus 0 C2 is 0, plus 0 C3 is 0. So you get 0 equals 1. Is that true? No, like we said yesterday, not unless you've been drinking. This is actually a contradiction, right? And so now, instead of just saying no solution, right, what we need to do is we need to answer the question. I mean, it's not possible to write U as a linear combination of V1, V2, and V3. Cool, cool? All right, so now on to the next thing. What the heck does it all mean? Well, here we go. Any vector space consists of 4 entities. A set of vectors, a set of scalars, and 2 operations. Currently, we are only exploring the vector space Rn, but you'll get really good at this stuff, you know, all the next really abstract stuff that comes. And so then when we get to more complicated vector spaces, this should be easier for you. All right? So I hope you have a wonderful morning, afternoon, or evening. And if you like what I'm doing, please subscribe. Have a wonderful day. Bye.